Hello everyone, welcome to episode 6 of Top Notch Science. I'm your host Joe Blazak, and today we're going to go over some news from the SLAC National Accelerator Laboratory in the USA. Now there they've created some of the shortest, purest X-ray laser pulses ever achieved. So to start off today, why is this news important and why should we care about it? Well, because of this ability to create these new laser pulses, we can actually open up a huge door to scientific discovery and help us create new medicines, new devices, and new materials. So how are they creating these new X-rays? They're taking another X-ray source, an X-ray laser called the LCLS from the same facility, and they're shooting it at a capsule of neon atoms. And these neon atoms, once they're hit, will send out a whole bunch of X-rays. And these are the new X-rays. Now you're probably thinking to yourself, why didn't they do this before? It doesn't seem like it's that crazy of an idea. I mean, someone should have thought of it. And it turns out someone did. Back in 1967, somebody theorized that this should be possible. But until now, until they had the LCLS, they've never actually had enough power in their lasers to accomplish this. So what's really going on here? Basically, every atom has a big shell of electrons around it. Now each one of the electrons in this shell has this very, very specific energy state. And what happens when the LCLS comes in and basically goes in, goes, knocks out all of the inner electrons in that shell, and then the electrons in the higher shells think, you know, I kind of want to be down there in one of those lower shells. Now it's perfectly fine for the electrons to do this, to jump to one of those lower energy states, but when they want to do that, physics comes in and tells them, if you guys want to do this, you guys have to do it all at once. You have to give up all of your extra energy to go to that lower energy state all at once. So the electrons look at this and think, how am I going to do this? How am I going to get rid of all this energy? I know, let's just throw it out. And what they do is essentially throw out a photon, a particle of light. Now it turns out that each one of these photons has a very precise amount of energy in it. Each electron that jumps down starts from a very precise energy level at the top and goes to a very precise energy level at the bottom. So when it makes that transition, the transition also has a very precise amount of energy. And it turns out that that precise amount of energy corresponds to a photon that exists within the X-ray light range. Now these new X-rays are very, very awesome for two reasons. The first reason being is that they have a much shorter wavelength than the LCLS X-rays, and that essentially means that they can allow us to see the details of much faster occurring processes and reactions. Now the second reason that they're much, much better is because they are more pure in their X-ray source. So essentially that means that you don't have a bunch of different wavelengths. Because of the way that the light is being created, you have very, very specific light ranges. And what that means is that the details of what we can see will be much sharper. So just think of it as a magnifying lens. Instead of seeing sort of blurry image, you see a very, very focused image. Now in addition to that, we can actually use what we've learned here and use that on other atoms like oxygen or sulfur and create new X-rays that are even shorter wavelength and use those on things like even faster processes so we can learn about that. That pretty much concludes today's episode. You can look forward to another one on Friday.